So up to this point, we've just looked at charges in place mostly. I mean, we've talked about charges moving to get onto the capacitor plates. Now we need to think a little bit more about charges moving, and that gets us to current. So current is a measure, so here's sort of a cross-section of a wire, if we like. So a wire that's a conductor. And so when we have charges that are moving, so positive charges moving this direction, that would be the direction of our current. So current would be in that direction, the direction the charges are moving. And we think about it as sort of setting up an observer spot right here and saying the current is a measurement of how many charges go across this area, right, this circle here, in what amount of time. So if we count some number of charges, 5 per second, then that would give us our current. So this has units of coulombs per second, right? So the units of current are coulombs per second, and that is what we call an ampere, but we just call it an amp for short, and that's a measure of current. Okay, so 1 coulomb, which is a lot of charge, right? Because an electron is 1.6 times 10 to the minus 19. So 1 coulomb per second is 1 amp of current. Okay. And most chargers that you look at for your computer or your phone are 1 or 2 amp chargers. That's just to sort of give you a feel for that. So this current that we have that is moving charges in a conductor, this is new for us because what we've said is, well, in conductors, charges move very quickly. So we have no electric field, right? So the charges end up on the outside. This is a case where we're constantly pushing these charges to move because we've got a battery connected up. So I'm going to connect up my battery here. Okay, so this is a voltage. That will create actually an electric field to move the charges as we go along. Okay, and notice, I should point out, this is what's called conventional current. We know what's actually moving are electrons, and so they would go in the opposite direction. So the direction we call current is the direction positive charges would go. So current is direction positive charges go. And even though what we know is moving is negative charges, that just means that the negative charges are going the other way. Okay, so if I have the positive end, for example, of a battery, then we're saying that's the direction that positive charges would go, or electrons are actually moving into this, to this plate of the battery. So the voltage provided by the battery is what drives this current to keep going. It sets up an electric field actually in our conductor, and then we talk about this often in terms of our current per area, and we define something called our current density, which is our current per area, and it becomes a vector because its direction is in the direction of current. Direction. Okay, so we could call it in terms of an I vector if you like. So this is current density, it's current per area, and it turns out that this electric field that gets set up, this electric field that we have, is proportional to this current density. Okay, so or the current density that we have, the current per area, it shouldn't be a surprise, depends on this electric field. And our proportionality constant is that we can say J, so this is in the same direction as your electric field if you want, because it's in the direction of positive charges. J is equal to sigma times E, where this is, I know we've already used this, this is called your conductivity. Or we can say J is equal to 1 over rho. This is sort of the more common one, and this is what's called the resistivity. Resistivity. Okay, and so to get an expression for your resistivity, how much this, whatever the material is, resists, if you will, current flow. In other words, it will take a bigger battery to create the same amount of current. If we have a higher resistivity, we can do a little bit of work in here. We can say, I'm going to bring this over here. So I'm going to have the resistivity. J is my I over A. Everything's in the same direction, so I'm just going to do this in terms of a scalar. This is my electric field. But if this is a nice uniform electric field, then I can relate my electric field to voltage and find your voltage is equal to this integral of E dot dl, if you like. But if E is constant and you know your length, it's just going to be E times L. So your voltage is equal to E times however long this is. This is my L. So in place of my electric field, I can have voltage per length. I'm going to put this in here. I'm going to have resistivity equals I over A equals V over L. Or I can rewrite this as V, I'm going to bring this L over here, is equal to then resistivity length over A times I. And this is what we call our resistance, capital R. And so we write, this is Ohm's law, V is equal to I times R, where this resistance is given by the resistivity. That depends on your material. Copper has a pretty low resistivity, which is why a lot of our household wiring is in copper, okay? And then L, that's the length of the wire over the cross-sectional area. So as we have a bigger area, it's a little easier for the current to flow. If we have a really long distance, this L, then that means we've got more resistance. And again, this resistivity depends on our material. In general, this resistivity is temperature dependent. It has some small temperature dependent. As things get pretty hot, then this resistivity actually increases with temperature. So resistivity does depend. Resistivity goes up as your temperature goes up. Okay, so, but this resistance often is just given as a value. And so notice this resistance, units of resistance, are just going to be volts over amps. But of course we give that a name, and that is ohms, which is represented by omega. That's the units of resistance. So you'll see that often, 100 ohms, 300 ohms. And so we can figure out how much resistance will, if I have a given battery, the amount of resistance really determines the amount of current that will flow. More resistance, less current flows. Okay, so to recap, current, which is represented by I, I'm not sure why, is our count of charge per time going across some area. It's really, of course, dq dt, right? Because a change in charge over a change in time becomes this derivative. We can say that V is equal to I times R. That's Ohm's law. It's really, it's an empirical law. It's not like Newton's law, because it only holds for what we call things that are linear, because this resistance, which is given by resistivity length over area, this really only holds for a constant value of resistivity. If our temperature is increasing or decreasing and this resistance is changing, we're not going to have a nice linear relationship, especially if things heat up when the current increases, as is often the case. So this works over a range of currents, but it doesn't work for all currents or for all materials. Some materials don't have this linear relationship. Okay, so those are our relationships. I'm going to say one more thing about working with current, hopefully to connect to something that you're familiar with, and that is power, right? So power, if you remember, is energy per time. That's what a watt is, right? And in particular, we often wrote it as the derivative of work, or derivative of energy, dt. And for voltages, if you remember, your energy, which we wrote as potential energy, was Q times V, right? That's how we get to energy, right? This is a joule per coulomb. Then I can put this in as dQ times V dt. And so notice, if your voltage is constant, like with a battery where it's a set voltage, and this becomes voltage dQ dt, and that's current. So my power then becomes I times V, or if we plug some things in, I can get different versions of this. So this can also be, if I solve, well, I'll put in for VIR, so it'll be I squared R, or it can be plugging in for the current here, V over R, it can be V squared over R. And so, for example, if you think about a 60-watt incandescent light bulb, you can say my power is 60 watts. I know the voltage is basically line voltage, call it 120 volts or so, and you can find out how much current you have going through that light bulb or the approximate value of the resistance of that light bulb filament. Okay, all of that comes from this relationship. Again, power is in watts. So voltage times amps turns out to give you watts.